Have you ever thought about how to walk? To get your foot to move forward, you need to rotate your knee. I would wager you probably never thought about how much to move your knee to get your foot to move forward. When it comes to walking robots, we may have a robot with a leg that has motors inside of it. To get the robot to move, we need to calculate how much to rotate the motors. Researchers have been studying this problem. Researchers at MIT proposed what I would call a physics-based algorithm. This models the contact forces between the robot's foot and the ground, and it uses a variety of optimization tricks to solve this quickly. This is in contrast to what I would refer to as a data-driven approach. This is where you might have a data set, like motion capture data of a real dog walking, and you might train a neural network to imitate this dog's movements. This project focused on something similar for the Biddle robot, an ultra low cost quadruped. How did we do this? Well, we started with that motion capture data of the dogs, and we built a simulation environment for our robot. Once we had that simulation environment, we could load in the data set of the dog walking, and we could map that to our robot. Why do we need to do this? Well, the robot is actually much smaller than the dog. The dog looks like it's big. It might be a German Shepherd. Its legs might be big. You can imagine it can put its foot down maybe half a meter in front of itself, which our tiny little robot can't do. So we need to map the motions of the dog to a sequence of poses for our robot. We do this by using some heuristics that calculate where the foot should be, and then using inverse kinematics to get the joint angles. We use similar tools to the ones Peng published with some slight modifications. Now, once we have this time series, we can actually use a technique called behavioral cloning to train a model based off of it. The key here is that we have this time series of states and actions. The states might be, where is our robot? And the actions might be, what do we do? So here you're actually looking at an example where I trained a neural network off of this data set, and now I'm running a live simulation where I'm asking the neural network what to do, given the robot is where it is. You can see the robot is slowly shuffling forward, but critically, it's not falling over. Now, this method does not perform incredibly well. It is slow, and it also does not move far. It moves about 0.15 meters forward in 5 seconds, but it hasn't fallen over. Now, the reason it hasn't fallen over is because I started the robot in an example that the model had already seen. So one of the disadvantages of behavioral cloning is if you move out of those examples, it doesn't work. So if I start this model with the robot laying on its belly, the robot falls over very quickly. An alternative model is an actor-critic model, where you're actually able to explore the environment and learn from that. Now, I used an implementation of a soft actor-critic model, and I didn't get this working too well, but we'll look at an example here where the robot is moving a little chaotically and using this to learn what actions might result in what rewards and what policies might be able to meet those rewards well. So in summary, we've looked at a variety of ways to control quadrupeds using learning, and especially for the ultra low cost Biddle robot. Thank you.